Good evening, ladies and gentlemen. Good evening all. Glad to see such a good turnout. Welcome to the Geological Society of London and to this, the third 2016 Society London lecture entitled Deadly Volcanic Flows, Understanding Pyroclastic Density Currents. My name is Malcolm Brown and I'm President Designate of the Society. And it's my pleasure to introduce today's speaker, Dr. Rebecca Williams of Hull University. Volcanic flows include lava flows, lahars, which are volcanic mudflows, and pyroclastic density currents, hurricanes of searing hot gas, ash, and rocks that swoop down the sides of a volcano during the most violent eruptions at speeds of up to 450 miles an hour and temperatures of up to 1,000 degrees centigrade, which makes them very difficult to observe and live to tell the tale. Even small flows are hidden in clouds of ash. The largest types of these currents, however, have never been observed at all, and no instrument exists that can be deployed to record them and survive. So what can we do to model these flows and help save lives? To try to answer this question, we welcome Dr. Rebecca Williams of the University of Hull. She first gained a BSc in Geology from Royal Holloway, an MS in Volcanology from Buffalo, and in 2010 a PhD in Volcanology from Leicester. Most of Rebecca's work now focuses on understanding catastrophic flows, and she's currently developing laboratory analog modelling techniques that simulate them. The extreme danger of these events means that they are not easily studied firsthand. Interpretations of these deposits are therefore often poorly constrained. Analog modelling, she believes, will help us bridge the gaps between field studies, theoretical computer models, and real-life events. Ladies and gentlemen, please welcome Dr. Rebecca Williams.
Thank you very much for the introduction, and thank you everybody for coming this evening. So, what do I mean when I say pyroclastic density currents? These are turbulent, density stratified flows that come out during volcanic eruptions. And you can see one here. This is a picture of a pyroclastic density current flowing from the Soufriere Hills volcano in Montserrat. And it's actually flowing within a valley. And what you can see here is the ash cloud that rides above it. Pyroclastic density currents are hot mixtures of gas, ash, and rocks. So all the things that come out of a volcano during an eruption gets caught up in these flows, and they travel down the slopes of volcanoes. Since about 1600 AD, they've been resulted in deaths of around 92,000 people. So they're the most devastating type of volcanic phenomenon. So around about half of all deaths due to volcanic eruptions has been accredited to pyroclastic density currents. So they're incredibly hazardous events. They form in several different ways, and their origins in many ways dictate how they flow and how they behave. So I'm going to be talking mostly about pyroclastic density currents that either form through lava dome collapses, and this is where you have a lava dome forming at the top of a volcano, such as an andesitic or a rhyolitic volcano. And what happens is the lava dome becomes unstable and essentially avalanches down the side of the volcano, generating these flows, and these are highly unsteady single surge currents that often flow down the valleys around volcanoes. I'll also be talking about pyroclastic density currents that come from eruption column collapse. So during our biggest explosive volcanic eruptions, the Plinian eruptions, you get these large eruption columns that form during the volcanic eruption. These are often termed umbrella clouds, after Pliny the Elder, during the Vesuvius eruption, described them as these umbrellas. If the column, however, can no longer remain buoyant, it starts to collapse. And then it starts to travel, sweeping down the sides of the volcano in all directions, so often radially away from the volcanic source. And these are much larger and much more hazardous than these smaller events. Many of you will be familiar with the Mount St. Helens eruption, and this was a particular style of eruption called a lateral blast, where the side of the volcano collapsed, sending out a supersonic jet up the side of the volcano sideways. And this generated highly steady, incredibly fast pyroclastic density currents. As you can see, they're formed in different ways, and this then means that they flow in different ways. So these are often confined to valleys, where this style and this style will often overtop all topographic barriers and flow out in all directions. Lava dome collapse pyroclastic density currents will be full of blocks of the lava dome, and then the ash that's generated when those blocks bash together. Whereas the currents that form from fountain collapse will contain all those things in that fountain. So we're talking about lots of hot gas, ash, pumice, and the lithic clasts, which are ripped up from the volcanic conduit during the eruption. This is a picture from Mount Sinabung in Indonesia in 2014. It's still erupting now. And this is a pyroclastic density current which is swooping in this direction, so not towards this lady who's running away from it. And the reason why they're so deadly is for a few key factors. First of all, they can be incredibly fast. So the small lava dome collapses to typically 30 to 60 meters per second. But at Mount St. Helens, people think that they've traveled up to 150 meters per second, so that's over 300 miles an hour. And then in some of the biggest currents in the geological record, they've been calculated to have flown at over 300 meters per second. That's almost 700 miles an hour. Because they're occurring during volcanic eruptions, they have the temperature, the magmatic temperature, so that's around 800 to 1,000 degrees C. And they can also travel incredible distances. So typically they travel around 20 kilometers. So if a volcano is to erupt right here in Burlington House, that would fill up on almost an area the size of the M25 circular. However, the largest ones in the geological record have been known to run out by over 100 kilometers. So again, if our volcano was to erupt here in Burlington House, that would encompass an area from Ipswich, Canterbury, Brighton and Oxford. And so these often give up huge volumes. So the largest known pyroclastic density currents have erupted volumes of around 10,000 cubic kilometers, which is around 9 million Wembley stadiums. And so they're fast and they're hot and they can travel huge distances, but they also have something called high dynamic pressures. And that's because they're very dense at their base. So if you have something that's very dense, that's moving very fast, they're incredibly destructive. So they can destroy all structures in their path. So to give you an example of how deadly they can be, I'm going to go back to Mount Pelée in 1902. This was an eruption on Martinique. And it's one of the first times that this kind of volcanic phenomenon really came to scientists' attention. This is Louis Cyparis. I'll talk about him in a moment. And he's overlooking what was the capital of Martinique at the time. The entire city was completely devastated, and over 28,000 people died in this eruption. And what you can see here is the foundations of the buildings that were destroyed by the pyroclastic density currents. Only 2 survivors from the city itself survived, although Louis Cyparis, after surviving the eruption, and the story goes, traditionally, that he was in prison, drunk, passed out, like this. And so he had terrible burns on his back, but actually being in prison probably is what saved him, because he was in a building that didn't have very many windows, and so the hot current wasn't able to get in to overcome him. He travelled America after this eruption as the sole survivor of the Saint-Pierre devastation. Although a few other people have kind of come to light since. Oh, no, I was there too. What we do know is that there were people outside of Pierre who survived, and we have an amazing kind of eyewitness account from a young girl, Habiba Ifril. She was actually not in the city, and she'd been sent out to her aunt's house. And this eyewitness account was taken after she was rescued. Just as I got to the main street, I saw this boiling stuff burst from the top of the corkscrew and run down the side of the hill. It followed the road first, but then as the stream got bigger, it ate up the houses on both sides of the road. Then I saw that a boiling red river was coming from another part of the hill and cutting off the escape of the people who were running from their houses. It was at this stage that she decided that running away was probably her best option. She knew of a boat that I think it was her cousin had, and there was a cave that she used to go and play in as a child. So she tried to get into this boat and she tried to row herself around the shore to this cave. But before I got there, I looked back, and the whole side of the mountain, which was near the town, seemed to open and boil down on the screaming people. I was burned a good deal by the stones and ashes that came flying about the boat, but I got to the cave. And then she was later rescued by a ship clutching onto the remains of the boat after this event. So I think this really demonstrates how terrifying and how catastrophic these flows are. But equally, many of you will know about Vesuvius, the eruption in AD 79 that destroyed Pompeii and Herculaneum. And many of you will know about the body casts that were found there. And these are really interesting because people used to think that these people died due to suffocation, so in inhaling the ash. But recent work, back in 2001, decided that actually they died through what's called thermally induced fulminant shock. Rather than giving you the definition of that, I've taken a quote from one of the authors of the study in The New Scientist. Within about 1 second of the heat wave striking, the victims' vital organs were stopped, their hands, feet and spines contracted, and their soft tissues were vaporized. So these are pretty awful events to happen. So what can we do to protect ourselves from them? Unfortunately, because they're so destructive, that doing things like building safety shelters probably isn't a wise idea. So they will completely destroy many of the buildings in their path. So really the only option we have of surviving these, unless you're a drunk prisoner, is to just get out of their way. So traditionally, what we would do is we would do some hazard mapping. So if we had an active volcano, we would go and have a look at the deposits. So doing very much geological mapping that's quite traditional. So you'd go around, find out the deposits, map their extent, and from this produce a hazard map. This has some problems though. Anyone that's ever done geological mapping will know that the exposure of the rocks is somewhat limited, and that there is actually huge gaps in your data set when you do geological mapping. There's particularly on many of these volcanoes are heavily forested, so they're in tropical regions, so actually the exposure is very poor. The other problem is that most of the exposure will be of the most recent eruptions and the most recent deposits. And just because a volcano has erupted in one particular way most recently, doesn't mean that that's the way it's always going to erupt in the future. So we have to think as volcanologists about a what-if scenario. What if the volcano is going to do something else? What if we don't understand fully the deposits that it's already formed, and therefore we don't really know what's going to happen in the future? So more and more groups who are working on active volcanoes are turning to using modelling techniques to generate their volcanic hazard maps. So this is a volcano hazard map for Colima in Mexico. And what they've done here is they've created these hazard zones for different events based on modelling techniques of computer simulations. This in itself, though, is a problem. Because how do we know how pyroclastic density currents behave in order to simulate them? If we're going to make a computer model which is going to predict where they might flow, and therefore we're going to use those to then make hazard maps to say whether someone's safe or in danger, we should be pretty certain that we know how they behave and how they flow and where they're going to go. But they're really dangerous, so we don't actually get to observe them very often. Direct measurement is hindered by many different things. So first of all, we need to be a safe distance away from an erupting volcano in order to survive observing a pyroclastic density current. This is a picture of Mount St. Helens. This is actually a pyroclastic density current which happened in August of 1980, so several months after the big catastrophic eruption. And this photograph is taken 5 miles away from this event, so probably at a safe distance. But actually, this photograph was taken from Johnston Ridge, so named after the volcanologist who tragically lost his life during the May 1980 event. So where it was safe to observe this density current, it wasn't safe to observe the density currents which happened during the May eruption. If you do get to actually observe one, though, and survive, the other problem is these currents are opaque. So what we're looking at here is the ash cloud that's surrounding the main density current. So density currents are stratified. So they're denser at the base and more dilute around their edges and at their top. And so what you're actually looking at here is the ash cloud that surrounds the density current. So whilst we can do video analysis, so this has happened a lot at Montserrat volcano, we're still only actually analysing the outer edges of the current, which may be behaving very differently to the inside. We can also go to a volcano after it's had a tragic event and try and map some of its destruction. So I've done this at Mount St. Helens and also more recently at Merapi. But that has a problem in that, again, you're only trying to understand the event that has just happened. And also, if you have a pretty devastating volcanic eruption, I don't think I'd want to be in the destruction zone to go in and map the destruction. So we need to find other ways of trying understanding these deadly events. And as good geologists, the first thing that we should also always do is go to the deposits. And this is my background. I'm a field volcanologist, and I tend to go out into the field, look at the deposits from these currents, and trying to interpret how I think the deposits were formed and what the current was like when it made them. So I mentioned how there were two main ways of forming pyroclastic density currents. There was the fountain collapse. So these would be very pumice and ash-rich deposits, and they form what's called ignimbrites. So here's a picture of a sequence of ignimbrites on Tenerife. One of my favourite locations, because there's this beautiful paleo valley here. So there's an ignimbrites filled up this paleo valley, and it sat on an ashy deposit and a pumice fall deposit. And actually there's 2 or 3 different catastrophic eruptions recorded in this sequence. Lava dome collapses will make deposits of big blocks of lava in an ashy matrix. But the characteristics of ignimbrites, so the sedimentary features within them, their composition, will depend on the origin, the flow conditions, and then the topography and the substrate over which they're flowing. So we can do some quite basic sedimentological techniques to try and interpret the deposits. If you were able, or if you wanted to, try and understand these currents, if you're able to anchor yourself on the ground during one of these currents passing. So these currents take about, from minutes to days time to pass over you. But if you were to anchor yourself there and not get whisked off in the 400-mile-an-hour current, or get your brains vaporized before you're able to make some notes, what you would find is that you were being slowly buried from the feet up. So these deposits progressively aggrade from the bottom. So the bottom of the deposit will record the earliest parts of the current, and the top of the deposit would record the later stages of the current. So we can look at vertical sections through our deposit to tell us what the current was doing through time. So here, perhaps we've got some cross-stratified ignimbrite here. So this tells us that to get cross-stratification, we need traction. So our current was probably dilute, because you need a sharp geological boundary between a current and an aggrading deposit. We're up here, it's massive. So in that sense, traction is dampened, and so you're not getting the sedimentary structures forming. So this part of the current was probably much more higher concentration. So our current that formed this deposit has changed from dilute to concentrated through time. And we can do this with different sedimentary structures, drawing on knowledge that we have from things like turbidity currents to try and interpret our deposits. We can also then look at how a deposit changes from near the volcano, so proximal, near source, to far away from the volcano at its end, distally. And what we find is that there is a grading pattern from proximal to distal. So density currents are made up of pumice, which is light, floats in water, but also ash and lithics, and lithics are very dense and heavy. So your lithics get deposited out in from your current near to the volcano, and then your pumice will travel much further and gets deposited out much further away. So you end up with a laterally graded deposit. So if you're lucky enough to get a complete kind of cross-section through the current from source to end, then you can say something about how that current has changed through space. And then what you can do is combine those two things. So here we have a current which is bimbling along, it's depositing its lithics close to source, and then its pumice further away. If our current changes in capacity, so say it wanes, so it's no longer able to carry its dense lithics far from source, what it does is it starts depositing those lithics closer and closer to the volcano, and at the same time, it'll also deposit its pumice closer and closer to the volcano. So you end up with vertical grading patterns as well as lateral grading patterns. So of course a current can wane, such as in this example, but it also can wax. So perhaps you could have your lithics carried further away. And so you can use these relationships to kind of reconstruct what the current was doing through time and through space. And what we're doing really is interpreting what we call lithofasces. And we're recognizing that because of the different lithofasces in a volcano, the current can be doing different things in different places at different times. But the important thing is the deposit can only tell you about a very small part of the current. And that is the part of the current which is forming the deposit. So basically the base of the current. We call it the flow deposit boundary. What we don't know is what's happening above that point. So our current that formed this deposit could only be a few centimetres thick, or it could be kilometres thick. We don't know from the deposit. The deposit only tells us what's happening in that flow deposit boundary. And then the other problem that we have is that if you have an ignimbrite sheet, which is the size of what's encompassed by the M25, you want to know what that current's doing across that whole area. You want to know if it's doing the same thing over here as it was over here. Because you want to be able to understand these currents in order to be able to assess what kind of hazard they might be if they were to occur again. And so you need to be able to understand the evolution of a current through time, but the problem is lithofasces are diachronous. So here we have a lovely cross-bedded ignimbrite, sat right next to a massive ignimbrite. So this current was doing two different things at the same point in time. So we can't use lithofasces to tell us about time, and we need something separate from that. And that's something I worked on with a team from Leicester. What we did is we found a ignimbrite which was chemically zoned. So magma chambers, and this is a pretty shocking diagram of a magma chamber, but they can be chemically zoned. So the composition of the magma can be different at the bottom as it is to the top. So if I was to start erupting this magma chamber, the first formed deposit will be drawing from the top of the magma chamber. So it would have the same composition as the top of that magma chamber. As our eruption progresses through time, it will draw to the next stage of that magma chamber. So the next part of the aggrading deposit will reflect that change in composition. And then as the eruption continues, what you end up with is you end up with a deposit that has a chemical composition which is the inverse grading from your magma chamber. And this is really useful because the chemistry changes from source. So it's an independent marker of time. It doesn't matter about topography, it doesn't matter about flow conditions, it doesn't matter about whether it's eroding or depositing. The chemical changes from source will end up all over your current. So it's independent from all those things that impact what a deposit will look like. And so this particular deposit that we used in our study was called the Green Tuff on Pantelleria in Italy. So this is Pantelleria Island. It's nice and small, which makes it useful for field studies. And it's sandwiched in between Tunisia and Sicily. So it's a lovely part of the world to work in. It's right here in the Mediterranean Ocean and the drowned Strait of Sicily Rift. And the deposits are beautifully exposed. So this is the Green Tuff here in this cliff section. And the Green Tuff is the youngest ignimbrite forming eruption. So it's excellently exposed across the island. It was reported to have formed during a caldera-forming eruption, although a lot of my work now we think differently. But we do know from previous studies was that this is a chemically zoned deposit. You'll notice that my ignimbrite looks a lot different to those ones that I showed you on Tenerife. That's because it's welded. So this density current, it was so hot when it was depositing that the ash shards welded back together. So we've termed Pantelleria the island of glass, because essentially these currents left a glassy deposit across the island's surface. But what this does is it records some really nice flow features, such as lineations, and you get rotated clasts, and you can do kind of microstructure techniques on this to get the kinematics, so it can tell you which direction the current's flowing at any one location. And it also means that it's nicely preserved. So we get the Green Tuff plastered on slopes up to about 80 degrees, which you wouldn't get with a cooler pumice-rich deposit. And we also have excellent field relationships exposed. So this image here, what it's showing you is there's a pre-Green Tuff caldera wall, and the Green Tuff drapes this caldera wall. So the volcano's over here, and this is the caldera wall. And so you can see the Green Tuff drapes up and over that onto the older stratigraphy. So this is one of the reasons we don't think that this was a caldera-forming eruption, is because we have the Green Tuff plastered against an existing caldera wall. And then there's later caldera infill through lavas. We have the same thing all around the island. This is Salta La Vecchia. It's actually a pretty dramatic cliff face. It's about 500 foot vertical cliff to my right to the sea. This is a spectacular location because, again, you have a pre-green tuff caldera wall, and there's about 30 meters worth of thickness of ignimbrite, which is ponded up against the caldera wall, and you can see it just here sneaking over the top as it was able to overtop that topographic barrier. And then we know from kinematics in the deposit that the current was traveling at this point from left to right through here. And so what I did was I found out what the chemical composition of the deposit was, and it was really nicely chemically zoned. I've chosen zirconium here because zirconium doesn't tend to go wandering off with weathering, but it's zoned in most of the elements that you can choose. And so we found that it had higher zirconium content at its base than it did at its top. And so we were able to turn that into relative time. So here we have zirconium and time, so start of the eruption and end of the eruption. So we arbitrarily divided up the zirconium into different time series, so 8 different time slots, because that was easiest to map. And then I went all around the island and took something like 500 or 600 samples, found out what the chemistry was, and then mapped out those different chemical footprints. And so where you had a particular chemistry, I was able to figure out where that would have been in time through the eruption, and then map out 8 different stages of where the current was flowing over the landscape at any one time. So the green here shows where the green tuff is exposed, but actually it's also beautifully exposed in most of the cliffs around here. Where it's white is where younger volcanic rocks have been plastered on top of it. So the next series of images I'm going to show you are the footprints of the current. And these footprints, we think, are only about 11 minutes in duration. And so the start of the current was actually pretty sluggish. So here we've got some caldera walls, and in most parts of the island, the current couldn't overtop them. They were constrained by that topography. Small fingers came out to the northwest and the southwest. This is pretty low-lying topography in this part of the island, whereas the south has got quite a lot of topographic barriers. So there's this big hill here, there's a whole series of cones along here and a large caldera wall. I've got different colours along the edges of the deposit, and this represents where we think the leading edge of the current is moving. So whilst a current is continuously coming from source, its leading edge could be stationary, so it's neither going further than it is at the moment. It can be prograding, so the leading edge is going further and further and further, or it can actually be retrograding, so it's actually not able to reach as far anymore. So green represents a prograding current, red represents a stationary current, and then blue represents a regressing current. And so you can see as we go through time, the current first of all inundates the northern half of the island, and it's still mostly constrained by the caldera walls of the rest of the island. And then as we move through time, the eruption continues to increase in explosivity until it starts to get to a kind of climactic phase where now we have currents going off in all directions, and it's starting to overtop some of these big topographic barriers. So it's topped over this caldera wall to the east, and it's now able to overtop this large hill in the south. And then you can see that at this stage, whilst it's still increasing, encroaching in some areas, it's already started to back off in other areas. And then there's only at certain points during the current's duration where actually the entire island is completely inundated by the current. And as the eruption starts to decrease, then the run-out distance that the current is able to travel also starts to decrease. So it's no longer able to top over those caldera walls that we saw. It's regressed completely away from this topographic barrier, this big hill in the south, until the end of the eruption is actually pretty sluggish, and there's only a few parts where the current is now flowing across the island. So this was really interesting because it told us 2 main things. First of all, the early stages of the current were really quite weedy. So this is only a little scoria cone here. It's only about 15 meters tall. Yet it was only the 4th stage of the current, whereas the current was able to get over this very small topographic barrier. The first couple of stages weren't able even to get over a 15-meter topographic barrier. And actually, this is the green tuff here. And if you look at some of the sedimentary structures in this part here, we have imbricated clasts, which are pointing back in the direction of the current came in, which tells us that the topographic barrier actually deflected the current back to where it came from. It also told us that the green tuff is a radial sheet around the volcano. And the traditional interpretation for this is that a current instantaneously, rapidly flowed out in all directions from the volcano and made this radial sheet all in one go. But what we actually found was that that sheet was built up gradually. It was a gradual inundation of the island. Sometimes the flow went in one direction, and then it shifted its path and went in other directions. And then actually, so here we have time, and then distance from the proximal to the volcano to distal. And there we found that the leading edge of the current prograded over the landscape and then retrograded. And this is really important when you think about mass flux. If you treat the ignimbrite sheet as a deposit that was made instantaneously, then you're massively going to overestimate the mass flux and the volumes and the velocities involved in your eruption. And we tie this kind of prograde, retrograde function to mass flux. So basically, if you don't have very much stuff coming out of your volcano, your current's not going to go very far. Where if you increase the violence of your eruption, you have a higher mass flux, your current goes further. So this is how you get the early stages of the current, your leading edge stays quite proximal to the volcano. The climatic stages, it travels much further, which gives us this prograding internal architecture. And then the late waning stages, our leading edge of the current starts to back up towards the source. So you get this off-lap internal architecture. And this is something that was predicted in modelling, but had never been demonstrated before in a natural current. So this is really great. And a lot of our field studies on ignimbrites are coming on leaps and bounds. There's been a huge paradigm shift in the way we interpret them in the last 20 years. And we start to think that actually we're interpreting these deposits and getting some really insightful information about looking at these things in the field. This is a picture of Mount St. Helens. What looks like matchsticks here is actually trees that were knocked over during the current. And you can use this to map out flow path directions from the current. But like I said, the problem with this is that the deposit can only tell us about the flow deposit boundary. And the other tricky thing is, apart from the fact that deposits are not very well exposed, pyroclastic density currents can erode as easily as they can deposit. So they often don't leave behind a record of their passing. But a lot of the lithofascist interpretations that we do, whilst built on very valid, good sedimentological principles, are actually based on conceptual models, because we can't stand there in a pyroclastic density current and actually see how a deposit's forming. We can't really see how those cross-bedding is forming. And so what we need to have is a way of trying to marry this up. How can we really understand how a pyroclastic density flows? And that's really important if we're going to build hazard maps, which tell people whether they're safe in one place or in another. So the first thing that we did to try and combat this was turn to analog models. So modelling turbidity currents has been something that people have done for many years. And this was the first way that people tried to model pyroclastic density currents. So what they would do was take a tank of water, and they would have a lock gate in one end and make a very dense fluid. And if you open up that lock gate, your dense fluid flows through your tank. And so you can look at the flow to try and understand the gravity currents. And so you can see one here. What you can see is a nice leading edge of the current with this nose. You can see a lovely mixing zone where our dense fluid is mixing in with the ambient fluid. We've got a body and a tail. And so this, in many ways, is very similar to dilute pyroclastic density currents, ones which are mostly ash and gas. And then people started to get a bit more sophisticated with these, started trying to add in particles, because obviously a pyroclastic density current contains a lot of stuff. And they started to try and put in lots of different sizes of particles to try and represent pyroclastic density currents better. And this gave us many really great insights. For example, it demonstrated that the density will impact on runout and velocity. So the higher the density current, the further and faster it will go. It told us that actually that really poor sorting you get in our deposits, the fact you have really big blocks and loads of ash, is really important on flow mobility. So if you put a lot of fine material in a current, the current will go a lot faster and a lot further. And then also it kind of proves some of our ideas that we had about normal grading patterns. So for example, do you remember how I said that pumices will get deposited a long way away and lithics deposited at source? You'd actually expect some of the really big pumices to be deposited out much earlier. They shouldn't be able to be carried that far. But the problem is if you've got a dense avalanche of material bimbling along the ground, and you're a nice fluffy pumice that wants to be sedimented out of a current, you're just going to get bounced back up by all those dense lithics. You're not going to be able to be sedimented. So you get what we call pumice bypassing. They get travelled further in the current than you'd expect. And we saw this behaviour in analogue modelling. Through time, the experiments became a bit more sophisticated and a bit more varied. People realised that actually kind of a dense salty fluid flowing through water probably wasn't the best analogue for pyroclastic density currents. So people started to model concentrated pyroclastic density currents, so granular flows, very high concentration flows. And through this technique, you basically get some material. So many people now use glass beads, although the early currents models would use things like rice or lentils or whatever they had to hand to try and simulate the different densities and the different shaped particles. And then what benefit this has is that actually you can model a column collapse. So you can have a column of material which you can essentially collapse to generate your density currents. So this was similar to that eruption column collapse mechanism. And they found that the kinematics, so the velocities and the runouts, very strongly controlled by the shape of the column, which is really useful because some of our biggest volcanic eruptions like Taupo, where it has a very high mobility pyroclastic density current, so it went on for 100 kilometers and scaled topographic barriers of over 500 meters. They think now, because of these experiments, was because they had a very high eruption column of over 50 kilometers, so it gave it very high kinematic energy. And that also, the ability of a current to flow is strongly dependent, again, on this mixture of fine and coarse particles. And then in more recent years, what people have realized is these flows here are what we call dry flows. Well, pyroclastic density currents are dry, but actually they contain a lot of gas. And hot gas is really important because it essentially acts as a fluid part of the current. And so in order to simulate these currents properly in the lab, you need to somehow fluidize them with gas. And so Olivier Roche's team down in Clermont-Ferrand have developed this technique of pumping gas into the analog current. So again, these are glass beads. Early experiments pumped gas with compressed air at the beginning, but Pete Rowley's work in more recent years has designed a flume which can continuously aerate your current, and that's by, anyone played air hockey? And you have that base, and it pumps up air, so it makes your puck hover, but they've built that kind of thing into their flume. So that makes a continuous aeration of your current as it flows through your flume. And what's really great about this is they've been able to generate currents which are very unsteady, which is the same as pyroclastic density currents. They wax, they weep, then they wane. And this has somewhat unexpectedly generated sedimentary structures in their analog models. So we have cross-bedding, we have prograde features and retrograde features for the first time as an outcome of these experiments. Kind of alongside this, some guys have gone one step further and developed an awesome toy. I shouldn't really call science a toy, but this would be awesome to play with. They basically take real pyroclastic material, real rocks, real ash, put it in a big cannon and shoot that stuff up to the sky and see what happens. And they're simulating different types of column collapses. And you can see that when that material comes to the ground, it hits the ground and travels outwards in a pyroclastic density current. So we're getting to the stage we're making very sophisticated small-scale analog models, but we're also starting to simulate real pyroclastic material. The tricky thing about this, though, is in order to make predictive models, experiments aren't really your answer. You can't make up a scaled model of a volcano and throw some granular material down it to see where it goes. So the reason why we do these analog models is to try and understand the physics behind them, actually try and understand how they behave. And we create numerical models to try and describe this behavior. So alongside the analog modeling, numerical modeling has also been developing. So people try to write equations to describe the underlying physics of these flows. And just the same as the analog models, it tends to be easier to either model dilute flows or concentrated flows. These numerical models can give us some really great insights. They can tell us about particle interactions. They can model things like the pore fluids and flow propagation. And they're very good at modeling one specific thing, so tracing one particular particle through a path, or perhaps telling you if you increase the size or the density of something, how is that going to impact the velocity of your flow. In more recent years, people have tried to tie together the idea that we now have that these flows are stratified. So Doyle and their team have been trying to couple together the dense avalanche at the base of the current and the dilute part of the current. And they've tried to take into account the fact that there's probably interaction between these two phases. And then where this is really leading to help us in hazard modelling is actually then taking these mathematical equations, of which there's pages and pages and pages to define one particular behaviour, and put them into some sort of computer simulation technique. And this is what people are starting to use to really simulate pyroclastic density currents. So again, they tend to fall into two different camps. You tend to have computer models which simulate our dilute flows, much more like ash flows, very turbulent, very well mixed, and they can tell us very well about things like flow runout and sedimentation. Or we tend to have a much more rock avalanche style flows. These tend to be very thin, concentrated flows, and these models are very good at telling us about things like inundation areas and velocity. One particular example is the Titan 2D model that came out of the Geophysical Mass Flow Group in Buffalo. Not necessarily the best flow model in terms of the physics, but what's really great about this one is they've made it completely open source, and they've put it online. So if you're a volcano observatory in South America or in India and Asia, you can take the digital elevation model of your volcano, so what the topography looks like, and then you can simulate different volumes and different sizes of flows across your landscape and generate these inundation maps. So this is the first step in seeing if an event's going to happen, if a current is going to form, where across the landscape is it going to go. And then much more recently, people have started to really put in some very sophisticated equations into these computer models. So this is a simulation of Vesuvius by Ongari's group in Italy. And this is a complete polyphase flow. So where I've said before that they tend to either do dilute or concentrate, and these guys have tried to combine those two things. They've used multiple particle types. So normally a model will only use like sand-sized particles or block-sized particles, because that's far easier to write the equations for. Where these guys use a whole mixture of particle sizes, and they take into account the fact that flows are density stratified and that you've got all these particles interacting together. And they've come out with some really nice data, but the problem with this is this only runs on a supercomputer. So most people around the world don't have access to a supercomputer, unfortunately. So there's this huge trade-off between how sophisticated we are in how we describe how these things behave and how we're able to model them, and actually the technological capabilities that we have to run these simulations. So where are we in terms of understanding pyroclastic density currents? Well, we have these numerical models that have become very sophisticated, but they still have to approximate physical behavior. It's just the numerical equations to solve them is just too complicated when you try and take in the huge variety of complexity of these flows. There's still some lack of consensus on the rheological conditions, whether they're dense flows or dilute flows, whether they're behaving this way or that way. And unfortunately, we're still somewhat limited by computing ability, although the technological advances hopefully will start to catch up with that, because it's come on leaps and bounds in the last few years anyway. Analog models are getting really great at simulating real pyroclastic density currents. But again, they're limited by this ability to simulate complex currents. So the ones that change in their concentration in time and space. And there's always this ongoing problem with scale. How much does a current that you make in a 2-meter flume tell you about a current from a volcano that travels 20 kilometers? So we have this problem trying to marry those things together. However, both techniques are giving us some real brilliant insights into pyroclastic density currents, and they're informing field studies. So we're able to recognize some things in the field and say, well, we saw that kind of being made in the lab, and we're starting to tie those things together. So where do we need to go in the future in order to understand pyroclastic density currents better? First of all, we need better mixing up of the fields, the analog and the numerical studies. So the numerical and analog studies need to much better take into account the complexity that as field volcanologists we're saying are happening in these currents. We need far better understanding of the interaction of pyroclastic density currents with topography. Most hazard maps are based on topography. So if you're one side of a topographic barrier, are you going to be safe during an eruption or not? Is your current able to swoop over that core zero wall if it wasn't there, or is it going to be reflected by that core zero wall? And then we need to be much better at acknowledging and modelling the complexity of these flows in terms of time and space. So one single flow can be behaving very differently in different parts of the current at any one time, and then that behaviour can change rapidly. So it can go from a very dilute current to a very concentrated current. It can increase its velocity, and it can change its devastation potential. And I think one of the only ways that we're really going to do this is become much better at quantifying the sedimentation of ignimbrites, which is then going to inform our field studies and then help improve, in general, our overall assessment of how these things behave. And only then are we going to have improved hazard assessments where people are much more comfortable about the hazard mappings that they're producing. And there was in Tenerife last week with the next generation of volcanologists, training them up on some beautiful ignimbrite sequences here, and maybe one of them will be able to answer one of these future research questions. Thank you very much.
Excellent, very good, very good. Questions from the audience? Can you just wait for the microphone and it's on recording.
Oh yeah, a couple of questions. One is the waxing and waning of the flow in the ignimbrite maps in the islands. What's that telling you about the dynamics of what the magma chamber is doing through time? So it kind of increases the mass flux and then declines. So do you know what the physical process is going on in the chamber to drive it?
Yeah, so it's quite well known that during an eruption, the violence of the eruption will change through time. And that could be through different reasons. So as you're tapping through different compositions, you're tapping through magmas with different volatile contents. So that might be triggering either a more violent eruption. Also, you've got things like as the eruption continues, the conduit of the volcano is being eroded. And so you're actually able to push out more stuff faster. So there is a whole, it's something that I didn't really kind of get into because actually the complexities of what's happening at source is probably controlling in part what's happening in the pyroclastic density current, but it's actually quite difficult to tie those two things together. But undoubtedly it has a huge impact on it.
That's one more quick one. Heat and pressure in the models.
Yes. Brilliant question. So we've recently realised how important the gases in these currents. So the analog models are trying to produce gas fluidized currents now. But the heat must be really important. That elevated temperature must be impacting the mobility and the cohesiveness of the flows. Actually, if you've got lots of fines material and a cold flow, it's probably going to clog up and decrease your mobility. Where if you heat that, it's probably going to increase your mobility. The difficulty is convincing someone to let me build a flume, heat it up to 800 degrees C and set it off. So I'm not sure, we'll have to answer those kind of things numerically, and there are people looking down that avenue.
Thanks. Another question, yeah. Thanks.
Hi, thank you. Clearly, mapping out the active flows is pretty difficult. I was just wondering if there's anything else that you can do to either see through the ash cloud or map it out. So any kind of thermal imaging, sort of radar, satellite maps, something like that, you can see either during or compare before and after.
Yeah, absolutely. So remote sensing now is a lot better. A lot of the active volcanoes have satellite passes over them, so you can map out the flows in that sense. They're quite useful in the fact that they destroy a bunch of stuff and leave an ashy deposit, so they're quite easy to pick up on satellite images. And then you can use thermal imaging to look at the currents. So they do this a lot on Montserrat. They have thermal imaging cameras set up. And so we get a good idea of things like the temperatures of the flows and the temperature patterns within the flows. But we still haven't really got a good way of kind of visualizing the current itself. So this problem with the fact that some parts of it are dense and some part of it dilute, that's all still hidden in the ash cloud. And as yet, there's no real way to see through that opacity.
Any more questions? I've got a question. On the Martinique one in 1902, most of the time what we're talking about is deposits. So this thing rushes down and leaves something there. But that one seemed to have it taken away the whole town, left the foundations. So actually, 50,000 years on, you wouldn't even know it had gone past. Are they just as common as the ones that deposit, the ones that erode?
Yeah, absolutely. So whether or not a current is eroding or depositing depends on its capacity. So if you've got a very fast-moving current which is accelerating, that's not going to be sedimenting out material. Yeah. It's actually going to be picking up material. So these currents are just as likely to erode as they are to deposit, particularly on high-angle slopes. Yeah. And this is one of the difficulties when you're trying to use the deposits to tell you about how a volcano behaves, is actually some of the most destructive flows are going to be the ones that are eroding. So they're going to leave no evidence of their passing. And so there's a huge chunk perhaps of our eruptive history that's missing, and that might actually be the most dangerous.
Yeah. So then do you find bits of country rock taken from here down there? So it's eroded from there and eventually deposited further down?
Yeah, so there's some really nice studies doing that. So it's very common to see if you go over a scoria cone, in the deposit behind that scoria cone, there's loads of chunks of scoria in it. Yeah. And there's been some really nice work by Gail Mahoods and Wes Hildreth, where they've actually used they've mapped out the different lithics and then able to use that to reconstruct where the current was going, where it's coming from. Yeah. So actually, in their case, they were able to show that it wasn't just one single vent that the current was coming out of. It's actually coming out of different vents and was picking up lithics from different parts of the volcano.
Yeah. Oh, good stuff. Last question from the floor? No? Oh, one more.
Just very quickly, the research you've been talking about covers a number of years, so presumably there have been situations where you've predicted a flow from a particular volcano. Have there been any instances so far when there's actually been a real eruption which you can compare with your predictions?
That's a really good question, and I'm just trying to think of any examples. So nothing that I've done personally, and I don't want to say something that's not true. So I do know of cases where actually what they've done really nicely for lahars. So they've used a two-phase version of the Titan model to map out the Ruapeo crater lake outbreak that happened a few years ago, and the model outputs from that really nicely matched up the predicted outputs really nicely matched up what actually happened. For pyroclastic density currents, off the top of my head, I can't think of a good example that's happened, although undoubtedly there are some. What people tend to do is they use the model to simulate flows of known kind of volumes and then compare that to where deposits of recent currents have gone. So they tend to do it retrospectively to validate their model rather than predictively.
Good. If there's any more questions, we'll be next door in the library for a glass of wine. But I'd like to thank Rebecca very much for a great presentation.